Join me in welcoming Richard.
The talk I'm going to give tonight is about nuclear fusion reactors in the private sector, because we're at a very sort of strange point in time where people are able to start financing privately nuclear reactors, mainly because fission reactors are obviously government business and they're regulated because they have weaponizable materials which private companies can never actually be able to use or get hold of. But suddenly fusion is involved, and the regulators are saying, yes, as a private company, you can go ahead and start building a fusion reactor. And so private companies are looking involved and say, well, is there some kind of Einstein eureka moment that needs to happen, and then we'll all have fusion? Originally, I used to think, this is such a wonderful concept, fusion. You've got something like this, which is a piece of iron meteorite, which is effectively iron cooked in a star. It's as simple as that is. You've got a star which is cooking hydrogen into heavier elements until eventually, as the star dies, you get, for a normal G-type star like ours, you get big chunks of iron. And when you're told that, okay, the sun rises and that's our large fusion reactor and all the stars are fusion reactors and effectively everything that you are, carbon, iron, oxygen, is all cooked in a star. It's not just a romantic wedding story. It's easy to forget that because it doesn't look like it. But when you see a piece of iron like this, you're reminded that fusion it's not just a technology, a sort of innovation that we all must sort of get our heads around. It is the technology. It is almost a new age. It's like coming out of coal. It's almost like humanity gets to a whole new level of science once we achieve this tech, but something is stopping us. And the public, no matter what perception they have of fusion, they seem to hold several ideas about it. This is what I think the public remember about fusion. So you've got Fleshman and Pons here. These guys actually developed what we call cold fusion, and a movie was made off that called The Saint, and people sort of seen it as sort of lightsabers. I think if you ask the public about nuclear fusion, this is the sort of thing that comes to mind. I'm going to assume that people at the talk tonight don't know a lot about fusion. I know some of you probably do know a huge amount about fusion, so forgive me, I'm just going to treat it as if you don't know anything at all. So we have nuclear fission as a power source at the moment, which is taking very heavy elements, and as they decay, we capture the energy. But typical of humans, when nuclear was in our reach after Einstein came up with E equals mc squared and that equation, the first thing we did was make a weapon out of it. And we used these very heavily enriched isotopes like uranium, and we enriched them further till we could make a bomb. But we also learned how to use it to make energy, and so we have fission reactors, why we just funded Hinkley Point C. Because it works, it's actually very clean, despite the history of fallouts and some of the bad press it has. It is actually one of our most important power sources, fission. Fusion is taking very light elements, like hydrogen, and cooking them into heavier ones, like exactly what the stars are doing. Now, that's a very, it's a very obvious effect we feel on Earth because the sun rises and we are hit with this amazing light coming from our fusion reactor. We all know that's what it does, but we can't really create a sun on Earth because we aren't not able to utilize that kind of gravity to force particles together. So for us to create a star, we need to make a device capable of achieving the temperatures or particle speeds on Earth, which is very, very difficult because what you're trying to do is bring particles together. And like particles, like hydrogen, don't want to come together because they are like, they have the same charge. So if, for example, you're driving around in your cars, you're trying not to hit each other. If I speed you up enough, you will eventually start colliding. It's just a question of how much speed before those collisions start to happen. It's pretty similar in the fact if you ionize particles and you speed them up enough, there is a point where they'll start to collide and fusion may occur. But how do we do that? What device is that done in? In the 1980s, Fleischmann and Pons, these two scientists here, Fleischmann on your right, used electrolysis to try and drive particles into the lattice structure of palladium, which palladium has got a sort of quite uniform lattice structure, and the concept behind it was that if you can bring particles or attract them into the center of the palladium and then apply something called superwave principle, which is sort of like shaking the particles together, you might be able to bring them close enough to fuse. In the 1980s, they reported heat coming from this reaction, which created an absolute uproar. People were saying, have these two people just created a star in a jar? And as wonderful as that sort of theory is, it was unable to be replicated. People tried to do that experiment again and again and again, and they couldn't reproduce those results. So Fleischmann and Pons were absolutely ridiculed, and they were discredited. And it was a big, people started saying cold fusion was a failure. The film The Saint is all about cold fusion. You can see this lady making a passionate talk about the cold fusion reactions she's detecting coming from this device, and eventually in the film it powers a light bulb. And unfortunately for Fleischmann and Pons, it still has not been proven that you can create star conditions inside an electrolysis type device. But there are people in Israel still pushing this science quite seriously. But on the whole, even today, fusion is still a little mythical and a little out there. It certainly raises eyebrows, and people think, well, it's the fusion energy it's the energy source of tomorrow and always will be. It's always going to be 30 years away. Billions and billions of pounds, lots of false starts. In fact, if the media hear about nuclear fusion, they automatically put the skeptical face on, and it's almost like if you say statements, you make statements about nuclear fusion and you're wrong, you're going to get slammed down and disgraced. But humans, everything we do is learnt from trying something and failing it. It's not about getting it right first time. It's about going in and making mistakes and making more and more and more mistakes. You shouldn't be smashing people to pieces and taking away their doctorates and having an uproar just because they got it wrong. Fleischmann and Pons were very optimistic with a technology that was, that if we could have a star in a jar, it would be the best thing humanity has ever done. So perhaps that contributed to how hard they were beaten down when the results weren't replicatable. But there are ways we can do it. So let's just talk about this. Here's a nice picture of the sun. That's nice. So that is our local fusion reactor. And the sun is effectively cooking hydrogen into helium. So it's bringing protons together, and the weight and the gravity behind it is so much that we can actually accelerate it is accelerating. The ions inside it are getting close enough to fuse, and there are billions of fusion reactions happening every second, and of course we can see the result of it. All the stars are fusion reactors, and all the elements around us apart from hydrogen and helium are cooked in the star. So we know that fusion is pretty prevalent in our universe. And it's enough to keep scientists pretty captivated. There's a big nostalgia around fusion for a very good reason. It seems to be the ultimate energy source. And well, it is the ultimate energy source. It's what the universe is telling us to do. You look at the stars, we've always followed them for direction. We should be emulating them. And it's fairly clear. But how do we build a star on Earth? How do you compensate for the fact that you haven't got this, you haven't got gravity at your disposal to create a star and crush particles together? It's a fascinating challenge and prompted many, many innovations from almost a century now. People have been working on this problem. The key part, the thing that's working in our favor, is that particles are charged, therefore you can confine them in a magnetic field, and you can hold them in a magnetic field and heat them up to enormous temperatures, and once they're ionized, which means you've stripped away the electrons from them, you can confine them with inside it sort of several devices. I'm just going to skip a few slides here. So this is one of the earlier devices that scientists tried to look at. Well, what they did is they created electromagnetic fields, and you've got a magnet either side, and you have a plasma, which is effectively your fourth state of matter. So you've got solid, liquid, gas, and a plasma. Eventually you speed the particles up so much that they become detached from their electrons, and you have this plasma, which behaves a little bit like a liquid, a little bit like a gas, confined in your magnets. The problem with this is, how do you plug the ends of it and keep the plasma in the center? And people were putting magnets on either side of their, this is called a magnetic mirror device, and you're basically trying to confine the plasma inside a tube. But the plasma wants to escape out the ends. And there's actually a saying with magnetic mirrors that you can tell how old the devices are by how many magnets are at either end, a bit like a tree. People just kept on adding more magnets, adding more magnets. But it wasn't very efficient. And this is one of the devices that people looked at in the 1980s. And another option was to bend the device around in a circle so that the plasma can be held in a magnetic, like a donut-shaped vessel, a vacuum vessel, and your charged particles can be confined inside a magnetic field, and they can rotate, if you like, so you don't have to worry about what happens at the edges, at the ends, which is a tokamak. This device is very famous now for anybody who's even looked at fusion. The device on the left is a sort of very simple setup of how that works. You can see the magnetic setup, the coils, and how the plasma is confined roughly inside a magnetic chamber. This is slightly more detailed if everyone can see that. But you're basically using very powerful electromagnets to... Do you want me to move this aside? You've got your donut-shaped vessel here, and your plasma of very, very hot particles, which you're trying to accelerate to speeds where they will potentially collide, and you're keeping them in place with these electromagnets. Now, if the electromagnetic field stops, your plasma will stop and your reaction will terminate. So this was one of the earlier concepts, actually, that showed promise. And this is a more recent reactor. This is JET in Culham down the road, which is a $200 million reactor that has had a huge amount of success. In fact, in 1997, scientists extracted 16 megawatts of energy from this reactor, which is an awesome achievement. You can see this central column is a solenoid, which is, and the plasma is rotating, well, it's being confined around this central column and squeezed to the point where you get it up to temperatures of 200 million degrees plus, where we hope we might have some fusion reactions will potentially occur. But it's an amazing device, and to think in 1997 they extracted energy from it is really very, very impressive. But in 1997, really, sadly, who really cared that much? We had fission online, which was doing very well. We had oil, which we weren't too concerned about. Global warming was sort of mythical. And fusion is expensive and it's complicated, and scientists are scratching their heads a bit with it. People were saying, you want to put billions of dollars in technology, and it's not a bomb, it's not a weapon. We can't, fission is a weapon. So there was an actual, a race of we have to have a fission bomb, no matter what, no matter how many billions it costs. Whereas fusion became a little bit of a science project, and sadly, it didn't get the same funding as fission. But governments were sensible enough to see that there is enough promise with JET, the Joint European Torus, which was in Culham at the time, to warrant further funding, because, were we to able to confine a plasma inside an electromagnetic field and reach temperatures where fusion can occur, we have absolutely solved our energy problem. It's not about how much energy anymore, it's suddenly humanity is faced with an abundance of energy, and the physics does support that. So the story is wonderful, and luckily, the juice is worth the squeeze for governments to come along and say, well, actually, we will fund a larger one of these devices. Why larger? In 1997, physicists learnt that plasma doesn't really like to be confined in a jar. Plasma is sort of, we don't see a lot of it on Earth, but in space, plasma is the most common element, the most common state of matter. In the JET reactor, the results were promising enough to say, we will one day be able to make a reactor that can confine plasma to the levels we needed. But it needs to be bigger because the plasma was experiencing turbulence. And the turbulence, effectively, it doesn't like being stuck in a tin and forced in with electromagnetic fields. And the turbulence was killing the reaction. So in 1997, the only way physicists could commit to stabilizing that or mitigating the problem of turbulence was to make it larger. There's a lot of science in gyrokinetics and magnetohydrodynamics for the theoretical physicists, which is immensely consuming theoretical physics, which is very hard to do on a whiteboard, because if you measure every block of plasma, as you start factoring in fusion reactions, you change the whole result. So it's very difficult for someone on a whiteboard, even though they still do it at Culham, to try and work out what and how plasma wants to be confined. Supercomputers show a lot more promise, but in 1997, effectively, the only way they could get around saying, look, guys, if we're going to fund this and we're going to put a lot of money behind it and you're going to guarantee it's going to work, making it bigger was the only real option. Another device that physicists came up with, which is rather interesting, is a stellarator. So one of the issues with having plasma in a donut is an issue of something called bomb diffusion, after a physicist called David Bohm. And as your ions follow the electromagnetic field inside the tokamak, they naturally want to move out towards the edge, towards the wall. And if your plasma is hitting the wall, you're losing the reaction, or parts of the wall or breaking off inside the plasma and ionizing and contaminating your plasma. And so really trying to keep them in towards the center of the tokamak is a challenge. And you can either add more magnets to the outside of it, but one solution was treat it rather like a scalextrics track, where you twist it into the figure of sort of an 8, and you try and bring the plasma back into the center so you can sort of keep it stable, which is a very elegant idea and received a huge amount of interest to points where people were making devices like this, which is the Fission Reactor in Germany, which is actually quite a recent one. Amazing. Because plasma likes to corkscrew through electromagnetic fields. It doesn't, it's a more natural flow. But as brilliant as this is, and Nobel Prizes being won for it, is that going to be a power station? I'm not sure it ever can be, because the price and the complexity, I mean, that is an amazing looking alien machine. But will BP be able to make these devices and start using them for energy? I'm skeptical. So we need a more simple device. One of the things that universities are looking at doing is making more powerful magnets and trying to hammer that plasma into submission. But the point of the Fission is that plasma would be far better rather than just add more electromagnetic power, which is meaning you're putting more power in, which means you've got to get more power out to achieve a level called Q, which is your break-even level of power in, power out. We just need to find a more simple, elegant device, and for that we just need to understand how plasma behaves under electromagnetic confinement. But that is an amazing device that exists now in Germany, and to give you an idea of how incredible it is, that is some images of engineers inside the Fission Reactor. And it is alien. But it's been built to try and handle how we simulate plasma would like to behave under electromagnetic confinement. And it has achieved some pretty interesting results. But again, as a power station, I can't see this being built all over the world. Whereas a tokamak will be and is being built. The great thing about tokamaks is they are showing enough promise, or they showed enough promise since JET in 1997 to warrant building a larger device. So, as I mentioned, scientists went to the government. They said, look, we've just extracted 16 megawatts energy from this fusion reactor. We believe this is the most important innovation of the century, and we would like you to plow in the money to build an absolutely giant device, which became known as Iter, which is the International Thermonuclear Experimental Reactor, or Iter as it's known by French people because it's built in Provence, or Iter if you're English. Iter is an enormous tokamak that was constructed and given the go-ahead in 2008. And to give you an idea of the scale, this is what we're looking at. A massive donut vacuum vessel trying to replicate the conditions inside a star. And that has been given the go-ahead at a cost of 13 billion euros. That's a person. So you can see how much faith people had in it, enough to warrant such an enormous device being built. Because it's actually, in a way, there's a saying that says, an elephant is a mouse built to government specification. And Iter has got all the hallmarks of that. It's oversized, it's overfunded. If you go to one of their sort of business forums, you see every piece of it was made in a different continent to appease the funders. So you see the magnets made in Japan, and some of the, well, I'll go into the different parts of what all the parts are called, but they are all built all over the world to appease the sort of funding agreement in order to get this off the ground. So it actually took 10 years for governments to even agree a location for this. It was between Japan and Provence. Eventually it went to Provence, and I think Japan got the Super Cameo Candy project or something to sort of appease them for not getting Iter. But the French wanted Iter, and they've got it. That's why it's called Iter. And this amazing giant is being built as we speak in Provence. And it's going quite well. That is our latest attempt at building a star on Earth. And if you look at it, it's cranes and cement mixers and lorries and magnets that can fit 100 people inside them. And they're all very pleased with this. And Iter keep posting pictures saying, here's one of our giant magnets and here's one of our giant cranes. But actually, since this specification was agreed upon in 2008, universities all over the world have started to do their theses on how plasma behaves in tokamaks and have said, well, actually, does it need to be this big? But it's too late to say, actually, no, let's make it smaller. You can't turn around now and say, okay, well, maybe we make it smaller. It is going to be that size. But the deal, if you like, for funding it, the deal for the 13 billion was it had to achieve a net energy gain of 10 times what you put in. So we call that infusion Q. So if you put in a certain amount of energy and you get the same amount of energy out, you've hit Q. Anything above that is a Q positive. Iter, the remit for building Iter was they had to achieve Q equals 10, so a 10 times net energy gain. And scientists back in 2008 felt comfortable that at that size, they could achieve Q equals 10. People say, oh, fusion hasn't been cracked. Again, like someone's going to have this amazing idea, and they're going to jump out the bath naked and run down the road and say, I've cracked fusion, and all of a sudden, fusion reactors are going to turn on all over the world. That's absolutely not the case. It is true that we have done fusion. We are actually quite good at it, but to get that level of a Q positive result, we've had to build a bigger device. Iter is the only game in town. All the governments have signed up to it, and our research facilities at Cullum and that at East in China, these are tokamaks that have been built all over the world, are now dedicated to prototyping for Iter. So they're not trying to achieve a net energy gain. They are working on how to better handle Iter when it turns on. Now, last year, Iter hit its halfway point. So, I mean, 2017, we're only halfway there. And this is where we are. This massive, giant vacuum chamber donut. But innovations are coming thick and fast out of universities and out of research facilities like Cullum. And even though they can't make it smaller, they are bettering our understanding of how to get the best result from Iter. And from the opinions of most of the leading scientists I know working on these projects right now, they believe we're more likely to get a Q equals 15 return. So imagine 2035 when this device is meant to turn on, or 2020, around that time, depending on how many delays and new parts and setbacks. And this thing has been the perfect storm for bureaucracy and delays, as you can imagine, especially with parts being built all over the place. But let's just say the press come along, okay, here we go, nuclear fusion again. Are we allowed to say this is, we finally ring the fusion bell? And yes, the inside trade, or what I believe, and what most scientists, all scientists working on this will tell you, is that Iter will not only work, it will surpass its remit in 2035. Now, Iter is the International Thermonuclear Experimental Reactor. It's not actually an energy-generating device. It's just to prove out the concept. The government then planned to go on and build DEMO, which is a demonstration power station tokamak, in 2055. So really, we will be old or dead by the time that the government get on to build DEMO, which is very, very sad. And that is the government schedule. Build Iter, turn it on, prove out that we can make a fusion burn, I mean a Q-positive plasma burn, and then spend another 25 years building a fusion power station. So what's quite interesting is how do you get energy out of a fusion reaction? If we start with that. So you can see this, the plasma is illustrated in yellow. If you can get it to the temperature where fusion reactions can occur, you will create a massive amount of heat, and humans know what to do with heat. One thing we understand. And their plan is to just drive a steam turbine, and away we go. Which is a bit simple, really, considering how much technology has gone into making the fusion reaction. And we do that by fusing two products of hydrogen and super heavy hydrogen called tritium and deuterium. Now, the sun is doing proton-proton fusion, but we can't do that because we can't achieve that kind of temperature. And well, we can achieve that kind of temperature, but we can't achieve quite those conditions. What we can do is we can get two isotopes of hydrogen. One is deuterium and one is tritium. So you've got deuterium, which is a proton and a neutron, and you've got tritium, which is two neutrons and a proton. So you've got D and T, and that will go on to form helium-4 and a neutron, that is the fusion reaction this is trying to create, plus, what are we achieving here? 17.6 MeV. Sorry about that, if you can't see that. But effectively, if we can get deuterium and tritium close enough together in an electromagnetic field, they can fuse to create helium-4, an alpha particle, plus a neutron, which carries most of that 17.6 MeV. That neutron is not a charged particle, so it just whizzes out of it won't feel these electromagnetic coils. So the particle flies out in any direction that it does, and that speed of the neutron, the kinetic energy of that, will heat the walls of the reactor, and we can use that heat to generate steam. And that is what these reactors are trying to do, and that's what Iter's trying to do. The reason we're going for this reaction is because it's the easiest known fusion reaction to create, to replicate. Which is why, also, we have tritium, we can breed tritium. And the neutron will heat the outside of the tokamak, and again, we're fairly comfortable about what to do with heat. So that's our first goal. Now, when Iter does turn on, and the world suddenly say, you know what, fusion's real. Apparently, they've just turned on this massive reactor in France, and it costs 13 billion quid. And apparently, we can all talk about fusion now because apparently it works. And little kids will be coming up to you on the train and saying, have you heard about fusion? You say, bugger off, everyone's heard about fusion. And fusion, fusion, fusion. We won't have a reactor, but we'd have proven it out with Iter, and they will then hopefully have achieved the same notoriety as CERN and projects like that. But the question anyone in aerospace or finance or the private sector will ask is, well, how long is it going to take for us to have this as a power station? Why is it so huge? Why is it 13 billion? Can we make it smaller? Can we make it cheaper? Now, the answer to can we make it smaller is already yes, but can we make it smaller? You know, smaller and cheaper are almost the same thing. The problem with neutrons as your source of heat is that the neutron will fly out in any direction and bury itself into the wall of the reactor and sort of destabilize your reactor walls. That's why when we say, is fusion radioactive, nothing, I mean, it would be incorrect to say like fission, because it just isn't. But it would be wrong to say that fusion has no radioactive emission, because it does have a neutron emission. So we've got a very small amount of radioactive waste that we need to deal with, but we're good at that because we've learned through fission how to handle neutron emission. So yes, it's almost totally clean, but these neutrons are not ideal, because it means we have to change the insides of the walls, and we have to do that with robots because we can't send people in, which is very complicated and expensive and adds to the whole expense of the equation. And it means that people who have the idea of, I want to have a fusion reactor on my boat, or I want to have a fusion reactor on my house, or, I mean, people are going to ask these questions because, of course, they are. They say, how small can we make it? To slow a neutron, a fast neutron, like that comes out of this DT reaction, you need about 1 meter of steel. So no matter how, if you could make a nuclear tokamak, a fusion reactor tokamak this size, and you could make it work, you'd still need 1 meter around the whole device in order to capture the kinetic energy of those neutrons. So with DT, these devices are going to be fairly large no matter how you do it.